In this video, we're going to cover the topic of dielectrics within electromagnetism. And this can often be a very confusing topic for quite a large number of reasons because there isn't a very intuitive understanding of what's actually going on within a material. So you'll likely see lots of common equations being used to describe what's happening within a dielectric. But the intuitive understanding for why it happens the way it happens is quite difficult to understand with this topic. So in this video, I'm not only going to go through some of the equations we use to describe dielectrics, but I'm really going to drill down deep into what is actually happening and what is causing some of the various physical characteristics within a dielectric. So without further ado, let's get into it. So the very first thing I want to consider is what happens when you pass an electric field through any region of space. So in the previous couple of videos, we've obviously talked about what happens when we have a charge. Let's make a positive charge for now. And we know that the charge is going to emit an electric field radially. But we've only really talked about the charge. What we haven't really talked about is the space in which the charge is emitting the electric field. So the space in which all this electric field is occupying. So we don't really know kind of what's going on there. And we also haven't really thought about what is actually in this space, whether this is just a vacuum or whether there is actually some kind of material right here. So this could be a charge that's passing through, like, I don't know, rubber or water or brick or anything like that. We haven't really talked about how the electric field that we measure at this point here really changes when we have this material in place right here. So what I've been doing so far, this formula for the electric field, that being Q divided by 4 pi epsilon 0 r squared in the r hat direction, we've actually assumed that this is in a complete and total vacuum thus far. So we've been assuming that charges, if you measure the electric field at this point here, we've been assuming that all the space between the charge and the point where we're measuring is just a complete and total vacuum. And the term that's of interest to us is this little guy right here, epsilon naught. So far we've just been assuming this is some kind of constant. But epsilon naught, when we think about it, is called the permittivity of free space. And if we kind of just break that down a little bit, then we kind of know what this really means. It's the permittivity for an electric field to permeate in free space. And obviously this is going to be the thing that changes somewhat when we have a material in place, when we no longer have a metal. The other thing I want to show is what happens when we pass an electric field through a metal. So I'm going to take this exact setup of a charge, and I'm going to, instead passing the electric field through the vacuum right here, I'm going to put this metal all the way around this electric charge. So this charge is completely encased in a metal. So what's going to happen to the electric field? Well, we're still going to get this electric field being emitted by a positive charge right here. But let's think about what actually is inside a metal. Inside a metal, we have electrons that have become delocalized from their atoms where they came from, and they are free to move, which is how we can get an electrical current. And what's going to happen to a negatively charged electron when we bring this giant positively charged thing in place? Well, the electrons are all going to clump towards the positive charge right here. So all the electrons that are in the metal are all going to race towards this positive charge right here. And that is going to leave a deficit of electrons away from the positive charge. So you have a negative charge near where this charge we placed right here originally was, and we have a positive charge right here. And because electric field lines go from positive to negative, then there is going to be a field that is going to completely cancel out the field that we've just produced. So we've had our positive charge, which radiates outwards, but the electrons are all going to move so as to completely cancel out the electric field produced by the positive charge that we put here originally. So the net electric field in any metal is just zero, because there is so much charge within the metal so as to completely cancel out any attempted electric field coming from this positive charge right here. So this is a very key concept in electromagnetism, and that is that the electric field within any metal is just zero. There is no electric field can pass through, because the electrons, there is so much charge so as to completely cancel out this right here. So we have one extreme where there's no charge whatsoever, and therefore a positive charge placed in a vacuum is just free to radiate as much electric field as it can, given by this formula here. And on the other extreme, we have a metal where there is so much charge that the charge will just completely cancel out any electric field produced by this charge right here, this big charge right here, because of the electrons. Now, what happens when we have something between these two extremes? Well, this is what a dielectric is. A dielectric is any material which has some electrons around within the material, but it's not enough electrons so as to completely cancel out any positive charge right here. So there will be some kind of response within a dielectric, but there won't be as much response simply because there is not as much charge that's able to move within the material. And so dielectrics can sometimes be called insulators, because that's kind of what they are. They are materials which have an absence of free charge. And so therefore they can't stop as much a big positive charge from producing an electric field, but they can stop it more to some extent. They can stop it more than whether this charge was just produced in a vacuum. And it's important to note that this is a property of the area around this charge. We're not talking about the material of the charge. We're talking about the area around the charge and how that is going to influence our electric field right here. So let's, for now, just forget a little bit about putting any charges within the medium right here. What we're going to do is we're just going to consider the atomic structure of the dielectric and how this is going to work. So obviously all materials are made up of atoms, and atoms you can kind of represent as having a positively charged nucleus and a negatively charged electron cloud around them. See, electrons kind of orbit in probability clouds governed by wave functions. So rather than the solar system model, this model, we're actually going to be considering electrons as a cloud around the nucleus that is a cloud of negative charge. And obviously you're going to have loads of these around within the atomic structure. But because it's a dielectric, these electrons are bound to the nucleus, the positively charged nucleus of the atom. So unlike in a metal where you have delocalized electrons, these electrons, for the most part, and that's the key thing, for the most part, not for the entire part, are all bound to the nucleus of an atom. So you have a scenario that looks a little bit like this. However, you could in fact have a material that rather is comprised of individual atoms with electrons orbiting a nucleus. You could in fact have molecules. So you could in fact have something like water, where you have lots of molecules right here. And the key thing about water is that it's a polar molecule. And what that means is that there is a dipole moment, which we talked about in the last video, that is permanently across the water molecules. And that's due to the bond angle within water molecules. So this is with a material that's non-polar, and this right here is a material that's polar. However, both of these, as we'll see in a second, can be dielectrics. So even though at the start, with no electric field being applied, these might look slightly different because this right here has polar molecules and this right here doesn't have any polar molecules, you can in fact have a dielectric response within both. And the reason for that is because when we apply an electric field to this material right here, what is going to happen? So we have our atom, which has a positively charged nucleus in the center and the negative cloud of electrons that is around it. But when we apply an electric field right here, then the positive charge is going to displace slightly towards the negative end of the electric field. And all the negative charge is going to displace slightly towards the positive side of the electric field. Oops, should be the other way around, in fact. So the positive side is going to be attracted to the more negative part of the electric field, and the negative charge is going to distort slightly towards the positive. So there's going to be this kind of warping, distortion, and therefore you're going to have this kind of off-axial tilt within the atom. Now, if we think about what this is, we have a bit of positive charge towards this end, but we also have a bit of negative charge towards this end. So we in fact have partial charges that are induced by the electric field. And this is called an induced dipole moment. And this happens within lots of different types of molecules that originally did not have any dipole moment, but because of this electric field, this induces a dipole moment across the atom right here. And we talked about dipoles in the last video, so we know a thing or two about these dipoles, and therefore we can define a dipole moment P right there, which is equal to this displacement, which I'm just going to call x. So that's the displacement between the center of mass of this electron cloud and the center of mass of the nucleus, multiplied by the charge, which in this case is E, or times Z, which is the atomic number, because if you're going to have helium, then you're going to have Ze coulombs of charge. So you have a dipole moment that's been induced by the electric field. So what's going to happen is within the material, you're going to have dipole moments induced across the material, like this. So they're all going to align in the same direction. There's going to be a macroscopic dipole moment. There's going to be loads and loads of dipole moments all pointing in the same direction. And the same thing is going to happen with this, with the polar case right here. It's just beforehand, the polar case had randomly aligned dipole moments. However, if you apply an electric field, the exact same thing is going to happen. You're going to get a dipole moment, which was already there to begin with, but because they were all randomly aligned, like here, then there was going to not be any net dipole moment. However, apply an electric field, you are going to get a net dipole moment. So what we've shown is that applying an electric field to any material which contains atoms or molecules will induce a macroscopic dipole moment thing across the material. And what this is called a macroscopic polarization. And this is normally given the symbol capital P right here. So this isn't dipole moment, which is lowercase p. This is capital P. This is the macroscopic polarization. And you can kind of think of the macroscopic polarization as kind of like a density that's across any material. And in fact, the way it's defined, the macroscopic polarization, is equal to the number of dipoles per unit volume, so N over V, multiplied by the dipole moment of each individual atom or molecule right there. So you actually have this macroscopic polarization, which is kind of like the dipole density. So it's actually a bit like mass density in that it doesn't depend on how big your material is. You have a polarization which is a property of the density of dipoles right here. And oftentimes you won't actually see the volume term written. So this, what you'll mostly see is that this is written as simply N multiplied by P, where N is simply the number density. So it's the number per unit volume of dipoles. And this is the polarization right here, the macroscopic polarization. So now I want to ask, what is the electric field at any point within this dielectric material? If we have an electric field that's been applied by, say, a capacitor or a parallel plate or just some kind of battery in general, what is the electric field that's within this point right here, within the dielectric? So what we said before was we had this external field, but because we have a response from the material, we actually have local electric fields within the dielectric that combine to make this kind of net electric field, which is in the opposite direction of the electric field that we applied originally. Because of course, the positives are going to be attracted to the negative end, and the negatives are going to be attracted to the positive end. And so therefore you have an electric field which is in the opposite direction, going from positive net to negative within the material. So this is the induced electric field, and we're going to call the external electric field just E external, right here. And so therefore the net electric field within the material, that any free charge which placed in this dielectric material will experience, is going to be just the addition, the vector addition of the external electric field and the induced electric field caused by the charges within the dielectric. So at this point, I'm going to make a key distinction. These charges are within the dielectric. They are part of the material of the very dielectric. So they are separate from any free charge which I could decide to place within the dielectric right here. And this is the thing that will experience the net electric field. But it's important to realize that there are bound charges, which is what we're talking about within the material right here. And there are free charges, which could be something that I could decide to place in later for whatever reason. And just to clarify, within a metal, the electrons, they are technically bound to the metal, despite the fact that you might call them free because they are delocalized. They are technically bound charges because the bound charges move so as to oppose any electric field, causing no electric field. So we have this equation right here, but we said that the induced electric field is caused by the macroscopic manifestation of all of the dipoles aligning together, which is causing a polarization, capital P, right there. So in fact, we can, instead of writing the induced electric field, we can write that the net electric field is equal to the external electric field plus the polarization divided by the permittivity of free space. Now, the reason why we divide by the permittivity is to keep the dimensions consistent. However, you can just think of the induced electric field and the polarization as being simply related. And we'll actually go into more about the relationship between these two quantities later. However, the dipole moment, if we have a look, runs from negative to positive. So that is the way in which dipole moments are defined. But when we look at the induced electric field, we can see that runs from positive to negative. So in actual fact, we have to put a minus sign right here so as to account for the direction of the dipoles, which is the opposite direction to the electric field in which it's applied. So you have that the net electric field is actually the external electric field subtracted from the induced electric field. And so what we can do is we can rearrange this equation to make the external field the subject. So E external is equal to the net electric field plus P divided by epsilon 0 right here. And now I'm going to multiply everything by epsilon 0. So we're going to have epsilon naught E external is equal to E net plus P right here. So I've just multiplied everything through by epsilon 0. And I'm now going to define D, capital D, as equal to epsilon naught multiplied by the external electric field right here. So this will just be this term in the equation right here. So let's go ahead and swap that in. So D is equal to E net multiplied by epsilon. Oh, there should be an epsilon in there. Plus P right here. And this is a very important equation that you guys will probably see a lot of the time in electrostatics. And this, basically what it's doing is it's telling you how you can account for the response that you'll find within a dielectric medium if you're trying to work out the electric field. And this D term right here, this term is independent of the material in which you are trying to work out the electric field. So of course earlier we said that if we wanted to work out the electric field, we couldn't do that because we didn't know whether it was a metal or whether it was a piece of rubber or it was brick or it was water or whatever. We didn't know how to account for that. However, this D term right here is independent of the polarization that you'll find within a dielectric material. It is independent of the polarization response that you'll have as a result of the atoms within a dielectric material. So what we're going to now do is we're going to integrate this equation over an area. So we're going to integrate this over some kind of surface area. So we're going to have the integral of D, and this is going to be dot producted with ds, is equal to the integral of epsilon naught times E plus P right here. So this is all going to be in brackets, and this is all going to be integrated over a surface right here. And now I'm going to break apart this integral right here on the right. So we're going to have epsilon naught E dot ds plus integral P dot ds right here. But this, of course, right here, we can recognize as Gauss's law. This is just the closed surface integral of an electric field over a closed surface. This is just equal to the charge right here. So this is the total charge that's within a surface. So this means that this term right here and this term right here both have dimensions of charge. And this goes back to earlier what I was saying about bound and free charge. This right here, this integral, is simply the bound charge within a dielectric. So this is the charge that isn't loose and therefore can't be felt by an electric field because it is bound to an atom or a nucleus, but it will still produce an electric field in response to an externally applied electric field. So this is the bound charge right here. However, we need to be a little bit careful, as we said before, because of course we have this kind of minus sign relationship between the dipole direction and the electric field. So this is in fact the minus of the bound charge right here. So we have this relationship right here. And so what's left over? So we have the total charge right here, and we have the bound charge. Well, what's left is going to be any free charge within the material. So that kind of makes sense because free charge plus bound charge is obviously equal to the total amount of charge. And so this term right here, this is all of the free or external charge that is enclosed within this Gaussian surface right here. And in the case of a vacuum, so if we have a completely clear medium with no dielectric whatsoever, so no atoms to produce any kind of dielectric response, then of course there's not going to be any polarization right here. And therefore, we're going to get that D is simply equal to epsilon naught multiplied by E. So this is going to be in the complete absence of any dielectric medium. And therefore, the electric displacement is simply equal to the permittivity of free space multiplied by the electric field. And similarly to Gauss's law before, we can in fact express this equation right here, that the integral of d dot ds is equal to the free charge. We can express that in differential form by writing that the divergence of the D field, the electric displacement field, is simply equal to the free charge density, which is equal to the free charge density per unit volume. So this is a very important relation right here. This is Gauss's law, but it can actually be applied to any material of your choosing. It doesn't necessarily have to be in a vacuum. So this is generalized Gauss's law. And oftentimes you'll see this as written as part of Maxwell's equations, because this is in fact the one that is universally applicable. The divergence of E equation is only applicable in a vacuum, which you'll very commonly deal with, but this is the universal one for electric fields that are propagating within a certain medium. So we have the equation D is equal to epsilon naught E plus P right here. And I also said that these are related to the various different types of charge that are contained within a dielectric. And I'm just going to prove this once again only in differential form, because we actually get some pretty useful equations in differential form for calculating the charges within a material. So I'm going to take the divergence of both sides. So I'm going to get the divergence of D is equal to the divergence of epsilon naught E plus P right here. So I'm going to take the divergence of both sides of the equation. And of course, divergence of D, we said, was just the free charge density within the medium. And when we apply the divergence, we're just going to apply it to each term individually. So we're going to get epsilon naught multiplied by the divergence of E plus the divergence of P right here. And so the divergence of E from Gauss's law that we had before is equal to rho over epsilon, where rho is the total amount of charge enclosed within a surface, or within an infinitesimally small volume in this case, because we're dealing with a differential form. But of course we're multiplying it by epsilon naught, so this is just rho. So we have the free charge term, we have our total term, and so all that's remaining is the bound charge, which of course has to be the total minus the free, and therefore this will be rho minus rho bound right here. So we can see that from this equation and this equation, we can get the result that the divergence of the P vector is simply equal to minus the bound charge. And this minus sign is again because of the polarization direction being in the opposite direction. So this is an equation you'll often see if you want to calculate the bound charge within a certain dielectric medium. You take the divergence of the polarization field. Now, experimentally, what has been shown is that the polarization right here is proportional to the electric field. So we have an externally applied electric field, and the amount of polarization that we get is directly proportional to the electric field that we apply. And the constant of proportionality is actually something called the susceptibility. And the susceptibility, this is the electric susceptibility, is basically a measure of how well a material responds to an externally applied electric field. So this is equal to the electric susceptibility times the electric field, and we have to multiply by epsilon naught just to keep the dimensions constant. But this term right here, the electric susceptibility, is a property of the material, and it's a scalar property in this case. In fact, you can actually get the this term being a tensor if you have a material that is not isotropic, but for this purposes, we're just going to keep it simple. So this is an experimental result. So how are we going to reconcile this with all that we've done so far? Well, we have that D is equal to epsilon naught E plus P, generally within a material. However, P, we said, was proportional to the externally applied electric field. So we're going to get epsilon naught E plus, and instead of P, we're going to write epsilon naught times the susceptibility times E right here. But we have common terms. So we're going to get epsilon naught E multiplied by 1 plus the electric susceptibility. So we have that D is proportional to E, with the constant of proportionality being 1 plus the susceptibility multiplied by epsilon naught. And what I'm now going to do is define epsilon as the general permittivity in any medium whatsoever. And this is going to be epsilon naught, which is the permittivity of free space, multiplied by 1 plus chi E, right here. And oftentimes you'll see this 1 plus chi E actually written as epsilon R right here. So epsilon R, the R stands for relative. So this is the relative permittivity. And this is basically the scaling factor that you need to multiply by in order to account for the material. And this is again assuming that you have an isotropic material. So you're going to get a lot of interesting equations right here, a lot of quite sort of fiddly, they're called the constituent equations. So you're going to get that D is equal to epsilon multiplied by E, where epsilon is equal to epsilon naught multiplied by 1 plus the susceptibility, which is also equal to epsilon naught times this epsilon R that we've just introduced right here. So I definitely recommend getting quite familiar with what each of these terms actually means. Chi is the proportionality relation between P and E, and epsilon is the proportionality relation between D and E, and they're related by this key equation right here. D is equal to epsilon naught E plus P, from which you can get things like the relative permittivity, which is the dimensionless permittivity, multiplied by the permittivity of free space. So epsilon with no subscript has the same dimensions as epsilon naught. Epsilon R is just a scaling number. It's a number that scales depending on how dense the dielectric medium is. And again, chi is just a scalar number as well. It doesn't have any dimensions either. So just to finish off, I'm just going to go through what a calculation of the electric field within a dielectric medium would actually look like. So you guys know how to apply the more general form of Gauss's law to any problem involving electric fields and dielectrics. So Gauss's law, as we said, was the integral of d dot ds, which is the same as what we had before for the vacuum case, is equal to the total amount of free charge within a dielectric. So let's take the case where we have a positive charge right at the beginning of the video. So this is going to be a positive charge, and it's being placed within some kind of dielectric, which I'm going to colour in green for now. So remember, the dielectric is the material that's surrounding the charge that I've placed within this medium right here. So the dielectric, as I said before, is going to have lots of bound charge because it has various dipole moments. But what I'm going to do is I'm going to ask myself, what is the electric field at this point right here? So how I'm going to approach this is exactly the same as using Gauss's law for a vacuum case. And I'm going to construct a sphere because, of course, we have a point charge which has spherical symmetry. I'm going to construct a sphere around this positive charge, and I'm going to work out what D is from this equation right here. So I'm going to call this positive charge just plus Q right there. And let's go ahead and start doing our integrals. So we have our integral of D. Now, because of course we only have a point charge, we only have a radial electric field. So therefore D is simply going to be equal to D in the r hat direction. So we're going to get dr, the r component, which is in fact the only component, multiplied by ds, which in previous videos we've said is r squared sine theta d theta d phi. So we're going to get a double integral right here, and that is equal to the free charge within. So therefore I can pull out all the constants out the front. This is an integral over theta and phi, so the constant is going to be dr multiplied by r squared. And I'm simply going to have the two integrals of sine theta d phi, and that is equal to the free charge. But this integral we've done loads of times before. The angles integrated across the entire surface of the sphere are just 4 pi. So therefore we can just, once you've done all the integration, you've done all the limits and stuff, you simply just get 4 pi. So you're going to get 4 pi r squared times d in the r direction is equal to the free charge. And therefore dividing everything by 4 pi r squared, you're going to get that dr is equal to the free charge divided by 4 pi r squared. And there we go, that is our electric displacement right here. And you can see that electric displacement actually has the same units as surface charge density, because this term in the denominator is just an area. This is in fact the area of the sphere that we chose to do our integration over. And so if you divide charge by area, you're going to get surface charge density. So dr is in fact a measure of the surface charge density. And as you can see, there is no epsilon within this equation right here. So the d is completely independent of the material and to do our integration over. So if we want to find the electric field, then we simply go back to using our constituent relations, that d is equal to epsilon naught e plus p. Doing the analysis that we did before, we actually also showed that d is simply equal to epsilon multiplied by E, and this is in the case of a dielectric material. So this is the case where you're not in a vacuum and the permittivity simply isn't just the permittivity of free space. This can apply generally. So all we need to do is we need to divide this equation by epsilon to get the electric field. So E, which is a vector, is equal to QF divided by 4 pi epsilon, remember it's not epsilon 0 because we're in a dielectric, times r squared. And this is going to be in the radial out direction. So as you can see, all that's changed when you add a dielectric is just the epsilon changes in this particular case. However, this is of course assuming that there is nothing but dielectric between the charge and where you're measuring it from. Things do in fact get a little bit more complicated when you have mediums which suddenly change. So say instead I have a positive charge and then I have a sphere of dielectric right here. So I just have a big chunk of sphere that is encapsulating this charge, which often happens within capacitors, particularly spherical capacitors. Then obviously you'd have to do the electric field within this dielectric and then work out the electric field outside this dielectric right here. This would involve doing 2 Gaussian sphere calculations right here. But of course, since you kind of know that the integration just leads to 4 pi, then you know kind of how it's going to work. And for this region right here, it simply will just be the case for a single point charge at a various distance. And the presence of this dielectric medium doesn't in fact really matter for anything like that. So that's how you'd approach a kind of dual problem like that with 2 different dielectric mediums. You'd evaluate it for each individual dielectric medium. And you'd simply get, in that case, if you had a sort of material which has a dielectric, but then the dielectric ends, and if you want to see what the electric field does as a function of the radius, then you'd get a 1 over r squared relation, which is something like that. But the point where you have the dielectric finishing, you'd actually just see a sudden jump in the electric field right here. So there'll be this sudden discontinuity within the curve. And that's because there's a discontinuity within the material right there. So this is at R, capital R, where capital R is the radius of the dielectric right here. So that's what you'd get if you were to measure the electric field, which has a dielectric, a finite sized dielectric encompassing it. So I hope that was a really useful video. I'm aware that this is a very complicated topic and it's very easy to get confused between the various different terms because lots of different terms get introduced in this topic. But I hope that was really helpful and I'll see you guys in the next video. Take care.